GCSE Physics boosters, nuclear radiation. What's that then? Well, it was discovered a bit more than 100 years ago, 1896, by this guy, Henri Becquerel, and it was discovered by accident. He was doing some experiments with some rocks that contain uranium, basically some uranium ore, and they were all wrapped up in cloth, and he put them in his drawer of his desk, but on top of some photographic plates. Then, when the plates were developed, there was some strange fogging on the plates. The photographic plates had been affected by something given off by the uranium ore. Now, about that time, radio was discovered, and they thought that it had something to do with radio, so they called it radioactivity. But of course, it doesn't have anything to do with radio, but the name stuck. Okay, it's nuclear radiation. It's nuclear because it comes from the nucleus. Yeah, it comes from nuclei, and it's nuclear radiation. Particles which come from the nuclei of unstable atoms. So, nuclear radiation comes from the decay of unstable nuclei. If it's unstable, basically that means it's not very well built. Maybe it's too big, or maybe it's got too many or not enough neutrons. Neutrons act a bit like superglue, holding the nucleus together. And if you've got too much or too little, then the nucleus may decay because it's unstable. Okay, and then after getting rid of this radiation, the nucleus becomes more stable. Decay is a move to stability. Okay, decay is a random process. We'll talk a bit more about that in another video. In other words, you can't predict when a nucleus will decay. It's a bit like throwing a dice. If you can predict when you're going to roll a 6, then you'd be very rich. Okay, and it's the same thing. It's a random process. One of the places that we get this radioactive stuff from is rocks. There are other places as well. There are gases in the air which contain radioactive nuclei, but you can get it from rocks, such as uranium ore. And what you do is you refine the rocks and you smelt them and you get this radioactive stuff out. And then in your physics lessons, they probably use sources like this. In that little metal thing there, there's some cobalt-60, which gives off beta particles. And it's kept in a lead-lined box so that none of this nasty, dangerous radiation can get out. Okay, so these radioactive sources. One way of detecting radiation is with a Geiger Muller tube, or just a GM tube. You might remember that Geiger was one of Rutherford's students. Now, it's usually connected to a counter which will actually count how many radioactive bits go in, or it can click at the same time, so this thing's going click, 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 click when radioactive stuff goes into the GM tube. And what we can measure is called the count rate. And the count rate is the number of particles detected in a certain time. For example, counts per minute. And that's called the count rate. Now, different to that is the activity. The activity of a source, in other words, maybe this radioactive lump of rock, the activity is the number of decays that occur every second. And that's measured in becquerel, named after that guy we met before, BQ, becquerel. Now, the activity and the count rate are different. The activity is going to be much bigger than the count rate because we're not going to detect every single particle that's produced. We'll only detect the ones that actually go into the GM tube. In fact, most of the particles probably won't even escape from the rock. Okay, so, but the activity is the number of decays every second. The count rate is the number that we detect every minute or second or whatever. Now, there's a lot of information on this slide, and basically you need to learn it all. Okay, I've put it all on one slide. It looks nice and neat. Get this learned. So an alpha particle, alpha, beta, gamma. Yeah, an alpha particle is 2 protons and 2 neutrons. It's a little cluster, a little honey nut cluster, 2 protons, 2 neutrons. So it has a charge of plus 2e. That means the charge of 2 protons. It's got a mass of 4 atomic mass units. Yeah, like protons and neutrons have the same mass, so it's got a mass of 4 atomic mass units. It can travel a couple of centimeters in air, just 2 or 3 centimeters in air, and it can't get through paper. So it's quite easy to stop alpha particles, and they don't travel very far in air, and that actually makes them the most dangerous, and I'll explain that later. Beta particles. A beta particle is a fast-moving electron. So it has a charge of minus e, a negative charge. Its mass is tiny, tiny, tiny. Yeah, the mass of an electron is about 2,000th the mass of a proton. It can travel 20 to 30 centimeters in air. And to stop it, you need like a few millimeters of something like aluminium would stop it. Some thinnish metal, a few millimeters of metal to stop it. A gamma, now I'm going to call it a particle because I do teach wave-particle duality. Strictly speaking, it's a wave. It's a little packet of wave energy called a photon, and it's a high-energy photon. It doesn't have any charge. It doesn't have any mass. It can travel a long way. I mean, how far can light travel? That's an electromagnetic wave. So it can travel a long way if it doesn't interact with anything. To stop it, you need lots of lead, lots and lots of lead. And if you had like 2-3 centimeters of lead, that would stop most of it, but some of it might even get through that. In fact, it would. Lots of information on that slide you need to learn. Now, these particles are dangerous because they are ionizing. Now, to ionize, basically, they bash into an air molecule or some other atom, and they knock off electrons. When a particle of radiation interacts with another atom, it will ionize it, and it will create what we call an ion pair. So you've got electrons floating around and positive ions. It creates ion pairs. And typically an alpha and a beta particle have about the same amount of energy, and they each will ionize lots, maybe thousands of atoms, like lots and lots of air molecules. But if you look on the diagram, you'll see that the trail of ions for the alpha particle is much smaller. Remember, it can only travel 2 or 3 centimeters in air. And the trail for the beta particles is much, much more spread out. Okay, it's to do with how heavy they are and how fast they're traveling. It's really getting into A-level stuff. But basically, alphas and betas are very, very ionizing. They ionize lots of atoms. Gamma photons, they are less ionizing, and they don't directly ionize atoms, okay? But they can still do a lot of damage, and they're very, very penetrating. They're very hard to stop.